Okay, we're ready to finish up our study of trigonometry as it relates to finding missing sides and missing angles of triangles. And our last thing today to talk about is some more application of where trigonometry is used in real life. Okay, before we can get to the actual word problem, we got to do some definitions. The first definition we got to talk about is a vector. If any of you have taken a physics class before, you have drawn vectors. A vector is a ray. It has a starting point and it goes on in one direction. And the arrow indicates the direction. Okay? Why are vectors important? Well, a vector is a measurement that tells both magnitude and direction. So the arrow tells direction. The magnitude is the size. So guys, a vector is like when we talk about driving 50 miles an hour and we're talking about drawing a picture of that, we would draw a vector. So the arrow would indicate what direction we're driving in, and the magnitude would be the speed, the 50 miles. Okay, so we use vectors a lot in physics having to do with forces, velocity, speed, acceleration. Okay, the other thing we need to talk about is a bearing. Bearing is the word that's used in navigation, and it's used in navigation for boats, planes. A bearing is an angle measurement, but it's very specifically drawn. When you talk about a bearing, you're talking about an angle that is drawn clockwise from the north ray. So, when you draw a bearing, you start with the ray that points to the north. So there's your vector that's pointing north. And when you draw a bearing, the angle always goes clockwise. So this angle here, we would say, is the bearing. So we could say it has a bearing of 40 degrees. So that's just a navigation term. So for today, for our word problems, you're going to hear the word bearing, and when we draw our pictures, we're going to actually put arrows because vectors are going to indicate the direction our boat or our plane is moving. All right, so let's go. I'm going to work two examples with you. We're going to do one of each. Okay, we're going to do first a boat, and then we're going to do a plane. So let's start with the boat. It says a ship leaves port on a bearing of 28 degrees and travels 8 2/10 miles. The ship then turns due east and travels 4 3/10 miles. How far is the ship from the port? What is its bearing from the port? So we have a two-part question. The hardest part about these applications is you have to come up with the picture. So don't look at what I have in the notes. Let's do this from scratch. So we have a ship and it's leaving port. So I'm going to put point P to mean the port. That's where we're starting from. And it says we're leaving on a bearing of 28 degrees. So the word bearing means an angle drawn clockwise from the north vector. So the first thing we have to do in this picture is we have to draw the north vector. So just like a compass, the north vector would go up, put an arrow, let's put the N for north. And now to draw this bearing, the terminal ray would go clockwise 28 degrees. That's your bearing at 28 degrees. So what happened? Here's the ship in the port. It's about to take off. It's not traveling straight up north. It's traveling on this angle. It's pulling out of the port a bearing of 28 degrees. Make sense? Now, it says we traveled for 8 2/10 miles. So it's traveling along this line of course at 8 2/10 miles. But does it always travel diagonally in this direction? No. At some point, after it travels the 8 2/10 miles, it says it turns due east. So guys, here's the boat in the port. The boat is going to pull out at a 28-degree angle and travel for 8 2/10 miles. Y'all with me? Then it's going to reach some point, and it's going to turn east. Well, east would be this vector. Make sense? And it says it travels due east 4 3/10 miles. So that's your picture. Everybody good? Now the question in part A says, how far is the ship from the port? So let's think. Here's where the ship started. Where is the ship now? Well, if you follow the course, it went here and here. So right now, we got a boat, a ship, right there. We want to know how far is this ship from the port. So that's what we want to find, this line segment. Y'all with me? This is our unknown. Everybody's good? If you look at that triangle. Is it a right triangle? No, it's an oblique triangle. That's why to find missing sides or missing angles, we're going to have to use law of sines or law of cosines. So that's why this is an application problem. Now, let's look at our triangle right now very carefully. What do we have labeled inside this oblique triangle? We have this side and we have this side. We have two sides. Is that information going to be enough to start law of sines or law of cosines? Heck no. To work either law of sines or law of cosines, you need three pieces of information. We know to work with law of sines, you either need angle, side, angle, 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 side, or our bad word, angle, side, side, which I'm going to write backwards because I don't like to write bad words. We know to use law of cosines, we either need side, 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 or side, angle, side. Well, let's think about this. We have two sides. So it's either this pattern, or it's this pattern, or this pattern. Well, could it be three sides? No, we're trying to find that side. So we know that's not it. So it's between these two patterns. To either use either one of these patterns, we got to find an angle in this triangle. To find the angle in the triangle is not trick, it's good old geometry skills. So this is where the hard part comes in, applying information you learned. If you look at this picture closely, you can form another triangle in this picture. If you take this east vector and extend it, what do you know about the east vector and the north vector? Oh, they're perpendicular to each other. So you know that angle has got to be 90 degrees. So you now see you have a right triangle here? Well, if that's 90 degrees and that's 28 degrees, can you find this angle here inside the right triangle? Sure you can, because you know three angles have to add up to 180, or we know in a right triangle, these two acute angles are complementary, add to 90. So what would you add to 28 to make 90? You would add 63 degrees. Make sense? No, I lied, 62 degrees. 62 and 28 would make 90. If this angle is 62 degrees, the angle right next to it, which is inside the oblique triangle, which is what we want, we need an angle inside here. These two angles are supplementary. They're a linear pair. They make a straight line. Supplementary angles add to 180. So 62 plus what would be 180? 118 degrees. So that, to me, is the hardest part. You're not always going to be given all the information you need to start working a law. So you're going to have to rely on your geometry skills. So again, we were given this angle, but that's not in the oblique triangle. We had the two sides of the oblique triangle, so we needed an angle measurement. The only way we could find that angle is if we extended this east ray and it intersected with the north ray. We know that's got to be 90 degrees. East and north are perpendicular. Now, if you look, we have side, angle, side. So now we know to find that missing side, we would use law of cosines. It doesn't matter how you label law of cosines. It doesn't matter if you start out with a squared, b squared, or c squared. It's up to you. If you want to actually start labeling these, I'm obviously going to call this side C. I'm going to call that side A, side B. It doesn't matter. But if I call that side C, then I know for law of cosines, I have to start out. C squared equals A squared plus B squared minus 2AB cosine C. I'd fill it in. I don't know that side. I'm calling side A the 8 2/10. I'm calling side B the 4 3/10. Minus 2 times 8 2/10, 4 3/10. Cosine, angle C is across from side C. So if that's my side C, angle C is 118 degrees. Make sense? Now, all we have to do is remember, we're trying to find C. Everything on the right side here is numbers. In one fell swoop, we can go to our calculator and type that in. So let's sit down and do that. Okay, what mode do we have to be in? Very good. We have to be in degree mode. I am in degree mode. So I type 8 2/10 squared plus 4 3/10 squared. I do the minus, the big minus, subtract 2 parentheses, because now I'm going to multiply 8 2/10 parentheses 4 3/10. I hit the trig function cos. I put in my angle measurement 118 and close it. I do not need the degree symbol. We're in degrees. We hit equals. We get this lovely decimal. So now we have C squared equals 118n. You write the whole decimal out. Do not cut it off. To get rid of a square, what do? We square root both sides. So let me go back to my calculator. I got to hit the square root button. The square root button is above in blue, so I got to hit second square root. I type the whole decimal in. Close it. That parenthesis says, hey, calculator, all that is underneath the square root symbol. And there we go. My exact answer. There's my exact decimal. They're going to ask you to round. I would assume because if this miles in tenths and this miles in tenths, they want this miles in tenths. So our distance from the port to where the boat is now is roughly 10.9 miles. 10 9/10 miles. Make sense? That wasn't hard. All right, let's go to question B. Question B says, what is the bearing from the port? So the word bearing implies an angle. So everybody look at your picture. Here's the port. The boat started off at an angle of 28 degrees, right? The boat is here now, which if you look, the boat's now bearing is that far. The bearing is always the angle from the north ray. So from the north vector, we started off 28 degrees due north. That's your bearing. Now I want to know, the ship is here. Here's my terminal ray where the ship is. This was still my initial ray. Now I want to know the measurement of this angle. That's the bearing they're talking about. The problem is, guys, don't do silly things. Just because this angle's 28 degrees doesn't mean that angle's 28 degrees. These are not the same triangle. They're not congruent. So guys, what we're going to do is we're going to have to find this missing angle inside the oblique triangle. I'm going to label it theta. Once we find this little acute angle inside the oblique triangle, then we'll add these up, and that will tell us now how far due north are we. Make sense? To find this missing angle, do we have to do law of cosines? No. Once we know this side, we can use law of sines. And we've seen that in the previous video. Once we do law of cosines once, we could always then go use law of sines. When I use law of sines, I need to set up two fractions, a proportion. Well, your proportion is going to be, obviously you want to find this angle, so it's across from that side. So that's how we're going to start. We're going to say 4 3/10 miles is the sine of angle theta. Your other fraction needs to be a side and an angle. Well, you know you had 118 degrees, so you need this side. Again, we're going to talk about this. Do you use the rounded answer, the 10 9/10 miles, or do you use the exact decimal? You always use the exact decimal. I know it's ugly. You got to do a lot of writing, but in real life, we want to be precise. How do we solve? Using law of sines, we cross multiply. That's our unknown. We want it on the left. So we'll have this big, long decimal. Sine of theta equals 4 3/10 sine of 118 degrees. Remember, you cannot multiply that number to that. That is an angle measurement. That's why it goes in front. To find sine of theta, we got to divide by this big decimal. We're going to divide. Miss Black writes everything on paper first before she ever touches a calculator. So the sine of theta is going to be 4 3/10 sine of 118 degrees divided by this 10 point, this lovely long decimal. Now we'll go use our calculator. All right? So we go to our calculator, turn it on, and we type what we said. 4 3/10 sine 118 degrees. Close it. Divide it by. We type that whole lovely decimal in. Do not abbreviate or cut it off. We hit equals. Our angle. Is that our angle? No, not yet. Remember, we've talked about this. Right now we have sine of theta. We change the fraction into a decimal. So we have that lovely decimal. Okay? So remember from our previous notes, when you're finding a missing angle, you change the fraction into a decimal. The only way to get an angle out of a calculator is not hit sine, it's to hit the inverse. So we want to do sine inverse. So theta is going to be the sine inverse of this decimal number. So I'm going to go back to the calculator. All right? I'm going to hit inverse sine. I'm going to type that whole decimal in. Y'all with me? Close it. Now we'll get our angle. That angle is in degrees because we're in degree mode, and it's decimal degrees. Okay? So now you'll have to read your directions. In your examples in your homework, they're very specific what they want. Do they want DD to the nearest tenth? Do they want DMS form? On this one, we're going to do DD to the nearest tenth. So our angle measurement came out to be 20.3820875 degrees. If I want to the nearest tenth, the 3 is in the 10th spot. There's an 8 behind it, so theta would round up to 20 4/10 degrees. Now, here's the problem. That's not the answer. That's the angle, the acute angle inside the oblique triangle. That was not the question. The question asked, how far, what is the bearing from the port now? The bearing from the port is from the north vector. What is that angle? So you would have to add the 28 degrees to what you just found. So 28 degrees plus 20 4/10 degrees, your bearing, you are now due north 48 4/10 degrees. Isn't that cool? Okay, so think about it. There's a lot of trigonometry in navigation. All right, let's look at one more. Let's do one that most of you may have experienced, flying on a plane. So let me erase. All right, the first thing you have to know is when you fly on this plane, there's a difference between airspeed and ground speed. Ground speed, obviously, is how fast the plane is going relative to the ground. So if you said the ground speed was 200 miles per hour, that means the plane on the ground would be going 200 miles an hour. Airspeed is relative to what's happening in the air. So think about it. When you go up in a plane, what affects the speed of the plane? Good, the wind. The wind either blows with the plane or against the plane. So if you're on a plane and the wind is blowing with the plane, that makes the plane go faster. So the ground speed, technically the speedometer may say 200 miles an hour on the ground, but because the wind is blowing it, the plane is going faster. That's why when you travel, a lot of times you usually get to your destination quicker. Just the opposite. Your speedometer on your plane could be saying 200 miles an hour, but in the air, the wind is going against that plane and it's slowing it down. So you have to be careful when we're reading these word problems that you listen to the vocabulary, ground speed and air speed. All right, so it says here, example 2. A plane with an airspeed of 192 miles per hour is heading on a bearing of 121 degrees. A north wind is blowing from the north to the south at 15 9/10 miles an hour. Find the ground speed and actual bearing of the plane. So we're going to draw a picture. All right, so you see the word bearing of 121 degrees. That's where I would start. You know to draw a bearing, you have to start with what vector? The north vector. So I'm going to put a point here. So this is the airport. Okay, that is the airport. That is the north vector. We know this plane is not taking off north. It is at an angle of 121 degrees. A bearing always goes in the clockwise direction. So now, guys, don't draw it like that. That's an acute angle. 121 is an obtuse angle. So what they're saying is, here's the airport. This plane is taking off in that direction because this angle is 121 degrees. Make sense? So here's the plane on the ground. It took off at this angle. So this is the direction it's traveling. That's why this is a vector. It talks about direction. This is the direction the plane is traveling. But the plane is not on the ground. Where is it right now? It's up in the air. So we know the airspeed is 192 miles per hour. Okay? What happens here, it says, the north wind is blowing from the north to the south. So you have to think about it. The plane was on the ground. It took off, going in this direction. It's flying, it's flying, it's flying. But the wind is blowing from the north to the south. So the wind is going this way. Well, think about it. If the wind is blowing north to south, and here's the plane, what's that wind going to do? It's going to hit the plane and keep moving it in this direction. Does that make sense? The plane ain't going up here. It's going to be going this way because that wind is going to hit it and push it. So we're going to draw that vector by saying, okay, here comes the wind. So do you all agree if that wind is blowing north to south? Okay, I'm just going to extend that a little bit more. Okay, that vector is showing I'm going south. When that plane gets into that wind, do we all agree that wind is going to push the plane down here somewhere? Okay, good. So the wind is blowing at 15 9/10 miles. That would be this length here. Okay? It says, find the ground speed and actual bearing of the plane. Okay. So first thing it wants to know is the ground speed. The ground speed is going to be the length. It's going to be the length from where the plane started to where the plane is now. So guys, look. Here was the plane. It took off in this direction. It's up in the air. It's up in the air. But this wind is hitting it. So what happens is this wind is blowing it. It's really not staying here. It's going off course and going here. So you all agree the plane, and I'm not the best drawer in the world, is somewhere there. When they ask for the ground speed, they're asking from where you started to here. This would be your ground speed. That's what they want to know right now, the length. So again, if you look, there is no way on earth that is a right triangle. That is an oblique triangle. We right now in this oblique triangle have this side and this side. Okay? We can't do anything with two sides. To use law of sines or law of cosines, we have to know three pieces of information. Right now, this angle of 121 degrees is no good to us because it is not inside our oblique triangle. So again, here's the hard part. Finding the geometry connection. How do you use this angle to get an angle inside the triangle? Well, again, it's about knowing geometry. If you agree, this vector here, the north vector, and this vector here that's going north to south are parallel to each other, correct? Parallel. We talked about this when we talked about angles of elevation and angles of depression. When you have in geometry two parallel lines and you intersect them with another line called the transversal, there is an angle relationship between the two angles that are alternate interior. Why do we call those alternate interior? They're interior because they're inside the parallel lines. They're alternate because they're on different sides of that transversal. The relationship is they are equal. Well, who says I always got to draw the parallel lines up and down? If I take that same picture and I draw the parallel lines like I have my vectors right here, and I draw my transversal in, I still have alternate interior angles. Here are the parallel lines. These angles are inside the parallel lines. They're on different sides of the transversal. Alternate interior angles in geometry are equal in measure. So if you look very closely at our picture, we have our north vector and our south vector. This line in red is our transversal cutting through. See that angle right there that's 121 degrees? It's above the transversal. So that means the angle down here below the transversal is the alternate interior angle. If that's 121 degrees, then that angle is 121 degrees. And that's the hardest part. The hardest part is not doing the trig work. The hardest part is drawing the picture and making the geometric connection with the angles. In order to use either one of these laws, you have to have three pieces inside the oblique triangle. This angle was not in the oblique triangle. It has a relationship. This is an alternate interior angle to this. So they are congruent, equal in measure. Now if you look, we have side, angle, side. Side, angle, side. So if I have SAS, that means I have to start with which law? Law of cosines. I want to find the speed, which is a line segment. I do not care what you label that. I'm going to label it this time, to just be fun, A. That means I would label this side B and C. It doesn't matter. But if I label it A, when I start out the law of cosines, I start out A squared equals B squared plus C squared minus 2BC cosine A. Whatever I start out the law of cosines with a side, is what I end with an angle. All right, I fill it in. A squared equals. I let my B be 192. I let my C be the 15 and 9/10. Minus 2 times B times C cosine angle A is across from side A. Your angle A is your 121 degrees. All my numbers are on the right side. In one fell swoop, I'm going to my calculator and typing this in. So here I go. Turn my calculator on. What mode do I have to be in? Degrees. And I start 192 squared plus 15 and 9/10. Oh, put the plus in this black. Plus 15 and 9/10 squared. Minus is the minus, the subtraction. Minus 2 parentheses 192 parentheses 15 and 9/10. Cosine 121, close it. I don't need the degree symbol. I'm already in degree mode. Hit equals. Oh, what a lovely decimal. We love these decimals, don't we? So A squared equals 40,261 decimal point. Do I want A squared? Heck no, I don't want A squared. I want A. So what am I have to do with it? I'm going to have to square root each side. All right, go back to the calculator. All right, so to get the square root, I'm going to have to hit second. Second square root. I type the whole decimal number in. okay? Typed it all in. Remember, those parentheses are telling us, hey, calculator, all of this is underneath the square root symbol. I hit equals. Okay, I'm going to write my correct answer, the exact. Now, depends on what they ask you to round to. Because this is in whole numbers, miles per hour, I'm going to go with whole numbers, miles per hour. If I wanted to know the ground speed, this is whole number, it would round up. So we would say the ground speed is approximately 201 miles per hour. Now let's think about that. Why is the airspeed different from the ground speed? Because remember, this wind is pushing towards the plane. So think about it. Here's the plane, and a gust of wind is pushing towards it. What's it going to make it do? That's right. It's going to make it speed up. Isn't that cool? All right, part B. Find the actual bearing of the plane. So let's finish it up. Bearing means we're finding an angle. So think about it. Here's the plane flying in the sky. The wind blows it. It pushes it off course. When it pushes it off course, is it still traveling at that angle of 121 miles? 121 degrees? No. It's pushed off course. So now your bearing from the north, the initial ray, is all the way here. That's what they want to know. They want to know how far off course it is. So think about this, ladies and gentlemen. If you're a pilot driving a plane, it's not just so simple as starting it up and taking off. You have to know about what the weather's doing and the wind conditions, because the wind is going to always throw that initial bearing off course. So there's a lot more to it, so appreciate your pilots. All right, so to find this whole bearing, well, first thing we got to do is find this little angle that's inside the oblique triangle. So I'm going to label it theta. To find this little angle inside the oblique triangle, once we use law of cosines once, we're done. Now we use law of sines. Okay, to use law of sines, if I want to find this missing angle, I got to use the side opposite. So we have 15/9 over the sine of theta equals. We know this angle, 121, so we got to use the side. Do we use the rounded answer, the 201 miles? Heck no. We use the exact decimal approximation, so you're not off. Okay, theta is what we want to find, so we want that on the left, so we're going to put that big decimal, that exact decimal, sine theta equals 15/9 sine 121 degrees. To get sine theta alone, we're going to divide by this decimal. We're going to divide by this decimal. Cancel out. Sine theta equals. Now, we know to find a missing angle, we don't want a fraction, we want a decimal. So that's why we need our calculators. Okay? So we're going to go to our calculator. I'm going to clear this out. We're going to type 15/9, the sine of 121 degrees, close it, divided by that lovely decimal. Hit equals. Is that your angle measurement? No. All you did was convert this fraction to a decimal. Are y'all with me? Okay, let me write that down. So we're going to write, so there's your decimal. All we did was convert this fraction into a decimal. Now, to get theta, we don't hit the sine button, we hit the inverse button, second sine. So we're going to say to find theta, we want to do the inverse of that decimal. And remember, we don't want to cut that decimal off. We want to use the whole thing so we get an accurate angle. So on the Pro, we double click to get the inverse. On the TI-30, we do second sign to get the inverse. All right, let me type that decimal in. Close it. Now here comes the angle. We know this is decimal degrees because we're in degree mode. Okay? So we get angle theta to be exactly 3.894711386 degrees. Then you just got to think about, read the directions, what they want to round to. For this one, let's round theta to the nearest whole number. So how many degrees is this as a whole? 3 would round up to 4. So this is roughly 4 degrees. So by that wind blowing towards the plane and pushing it, it threw it 4 degrees off course. So your new bearing is not 4 degrees. Your new bearing is all the way 121 degrees plus 4 degrees. So your new bearing due north is 125 degrees. Okay, we are done with our study of trigonometry as triangles. We are ready for our next major test. So you have to focus. We looked at this in components, pieces. First, we started out with right triangles and how to use trigonometry. You're doing the definition SOHCAHTOA. Changing, instead of using X, Y, and R, using vocabulary words. Then we talked about how if we have an oblique triangle, we cannot use SOHCAHTOA. So we developed the law of sines. Then we developed the law of cosines. We talked about the area, developing some area formulas related to trigonometry. And we finished up by doing some practical application problems in real life for you guys to appreciate how important trigonometry is in our real world. You cannot navigate without having a concept of trigonometry. You have a lot to go over. You got to know your 6 definitions: sine, cosine, tangent, cosecant, secant, cotangent, in terms of opposite, adjacent, hypotenuse. It's a lot of knowing how to work your calculator, as you know. So you got to know what mode you're in, whether you're in degrees or radians. You're going to type your angles in, DD, DMS. Okay? You have to know your law of sines and your law of cosines. You got to know your areas. You got to know some vocabulary. Take your time, practice, study. We begin our third part of trigonometry in the next lecture. See you then.